ahead of me here. Okay, so let's go up and then do another problem. Okay, move to. Okay. Okay, so now we take 100 bottles. Okay, you sample 100 bottles of detergent. Find out that the average bottle, I should change this problem one of these days, something that's a little more public health, related. However, this is what we got. You sample 100 bottles of detergent, brand A. I don't know why I didn't call that brand X, but brand A. And find that on average, each bottle will do 57 loads of wash, right? Some bottles do 55, some bottles do 57, so on and so forth, right? You know that the standard deviation for the entire production of 100,000 bottles is 5 loads per bottle. So what is this? The standard deviation of the population is 5, right? And 57 is that the average for the population? Mm-hmm. It's the average for the sample of 100 bottles, right? So what do we know? We know the sample average, X bar, right? And we know the population standard deviation is 5 loads either way, for these bottles is the standard deviation. So, ignore all the rest of this stuff about detergents and all the rest of this stuff. We don't really care about that. Okay, it could work with any normal distribution. Okay, so I'm going to go in here. I'm going to sketch this. This is my sample distribution. So what was the average for the population of bottles? It was, oh no, I don't know that, do I? All I know is my sample mean. What's my sample mean? 57, right? But I do know, and what's that? That's X bar. Okay, put it that way, or you'll see me a lot of times write it X bar if I don't have an easy way to write that bar over the top of it. Okay, my standard deviation now for all of these values for the population is 5. And what was my sample size? 100. Right? My sample size is 100. Okay, so now let me think about this for a second. Now, if I took samples over and over and over again, my standard deviation for my sample means my standard error is going to be 5 over the standard deviation of the population. It's going to be standard deviation of population over the square root of the sample size. Okay, it's going to be 5 over 10. It's going to be 0.5 or 1/2. That's my standard error, right? So right now, I say to myself, well, I took a sample of size 100, right? And this particular sample gave me a result of 57 average for that sample. Is that the population mean? We don't know. That's the sample mean, right? So now we took a sample of 100, we got 57. We say to ourselves, okay, that's my sample of 100. Well, at this point now, that's all I'd be able to say about this. If somebody asked me, well, how accurately do you know that it's 57? I wouldn't be able to tell them anything. I couldn't tell them I know it very accurately, I know it not so accurately, or I'm sure, or I'm 99% sure it's 57. It's 57. That's kind of clumsy, right? How about if I could at least give them a range and say, I got a mean of 57 from the sample I took. However, I can tell you that I'm 95% sure it's between 56 and 58. That's a lot better than being able to say just that it's 57 and you don't know how accurate that is. That's called a confidence interval. And we're going to use what we know about the way samples are distributed to create an interval where we have a certain level of certainty that the true population mean is within a certain range. So now not only can we say what our sample mean was, but what range that we expect with a certain level of certainty, with any level of certainty that we want to give it. I could say 95% certainty, 99% certainty, 99.9% certainty. What's the only certainty I can't say? 100%. Can't say with 100% certainty, right? But I can, depending on the sample size, I can make that range narrower or bigger depending on what the sample size is, because the sample size determines the standard deviation of the sample means, or in other words, the standard error. So let's give that a try. Okay, so now let's go back and see this problem. Is 57 mu or x bar? Well, we know that that's x bar, right? Which is a statistic, not a parameter. is 5 sigma or standard deviation. That's a statistic, right? That's the standard deviation because I said that it was the population, right? Calculate the standard error for repeated samples with this population. We just did that. It was 5. It was 5 over the square root of 100, which is 1/2. Calculate the 95% confidence interval for the population mean based on this sample. How am I going to do that? Well, let's see. I know that if I took repeated samples, I would expect that 95% of the results would be within 2 standard deviations below the mean and 2 standard deviations above the mean. If I want to be more precise, I would say 1.96 below and 1.96 above, right? Standard deviations, right? Okay, so now my mean, I'm estimating my population mean based on my sample will be 57. But let's, for the moment, assume that it's pretty close to that. So now, if that's true, what percentage of the samples would I expect to be 2 standard deviations below to 2 standard deviations above? Well, 95% of the time, we would expect our other sample means to be within that range. So what is that range? Okay, well, that range is going to be, let's see, I'm going to take the sample mean, 57, right? Minus 2 standard deviations, which is 0.5 minus 1. So 56, this value is 56, and 2 standard deviations, which is 0.5, above is going to be 58. I would expect 57. I would expect that 95% of these sample means, if I really got the population correct, I would expect 95% of these sample means would be between 56 and 58. I'm going to, from now on, refer to that quantity as my confidence interval. Okay, and instead of estimating it this way, I'm going to write a formula now that will calculate it for me. What is it going to be equal to? It's going to be equal to x bar, my sample mean, plus or minus my 1.96. Why 1.96? Because that's the range of z-scores below and above. 1.96 times my standard error, right? So what is it in this case? It's 57 plus or minus 1.96 times my standard error, which is 0.5. So if I really want to calculate this out, what it'll really come out to, get my calculator up again. Oh, it disappeared into the background here of something. What's that? Yeah, I'm looking for my calculator. You see it there somewhere? Where'd it go? What's that? On the right side? Ah, there it is. Okay. All right. So what did I say again? I said first of all I'm going to calculate 1.96. I'm going to clear my stored memory here first. Clear this. 1.96 times my standard deviation was 0.5. Okay, is equal to that. That's 1.96 times my standard deviation. I'm going to store that in memory. Okay, so now I'm going to clear this out, and my value is 57 minus 1.96 times my standard deviation. Recall memory. Minus recall memory. It's going to be equal to 56.02. And on the other side, it's going to be 57 plus 1.96 times 0.5, which is, recall memory, is going to be that. It's going to be equal to 57.98. See, if I use the empirical formula, it would have been just simply 56 to 58. But this is more accurate now. So now what does this range really mean? This range, we don't really know what the population mean is. So I can't really say for sure that this is the way if I took repeated samples over and over again, that they would really be centered on 57. 57 may be a low estimate of the mean. 57 might be a high estimate of the population mean. I don't really know. But what this will allow me to do now is say, if I start with 57, I know 95, there's a good chance that this was within 2 standard deviations, either below or above the true mean, because that's the way the distribution is. I'm 95% sure that value 57 is within 2 standard deviations below or above whatever the true mean, for the same rationale that I'm doing this. So that means if I create a confidence interval, 2 standard deviations above, 2 standard deviations below, in other words, 56 to 58, I'm 95% sure the true population mean is between those two numbers. Okay, that's very powerful. Now I can say our sample mean was 57. However, I'm 95% certain the true population mean is between 56 and 58, or the more precise numbers, 56.02 to 57.98. So that gives us a way to understand what our likelihood of being off if we assume that that's the population mean. Well, what good does that do us? Okay, so now let's take a look at the next part of this problem. Company brand B, brand Y, that was brand X, now we're going to brand Y, okay, is known to produce a product that washes 95 loads of bottle. Oh, wait a second. I'm changing that number because it's too big. I must have monkeyed around with this a few times. 59. I'm going to make it 59. Okay. Company B is known to produce a product that washes 59 loads per bottle. Can you say with any certainty that brand A goes further than brand B? I'm going to change that to 50, 55. Okay. Can you say with any certainty brand B we know is, average is 55. That's the whole population. That's every bottle of brand B. Does 55. Now, can we say with any certainty that this brand A does better than brand B? Well, I'm 95% sure that brand B will do between 56 and 58 loads. Brand A does 55. So I'm 95% sure that the average number of loads that I'll get from brand B is better than brand A is better than brand B. Get it? I can compare it to some known value. Later on, when we do this, that's going to be basically something called a one sample t-test, but we're going to get into that later on. So now, by having a confidence range for what our population mean is, it allows us to more analytically compare it with other populations. Okay, our confidence level is 95% that it's going to be it's going to be between those two numbers. Let's move on to another problem. Okay. First, before we move on to the problem, let me see if the people online are still there, still living, still awake, having a nice meal, relaxing. Okay, great. Okay, any problems with that so far? How about questions? Questions about this so far? Yes.
Just for the last question with brand A and brand B.
Yes.
So we said that brand B for 95.
I changed it to 55. Okay. I changed it to 55. Right? Because the number I've been monkeying around with. Sometimes what happens is that when I do the demonstrations another time, I change the numbers to make it a little bit different, and then I forget to go back and rearrange it. Yes. Yes.
Can we say that we're 95% sure that brand A will do more than brand B?
Yeah, there you go. Right? Because we're 95% sure that we don't know that the true mean is 57. We don't know if it's 56.9. We don't know if it's 57.2. But we're 95% sure the true mean for A is between 56 and 58. All of those possibilities are above what brand A does, right? What we're known for. That's the idea. That's what we're after here. Being able to quantify this so we can, quantify our level of certainty so we can compare. Now, that doesn't mean we can't be wrong by saying that, right? Because there's still 5% chance that it could be higher or lower than that range, right? So that's the problem with statistics and public health and epidemiology and so on and so forth. And that's why we wind up with studies where rats get cancer when they eat saccharin, and then suddenly somebody else does a study, and so on and so forth. And a lot of times we are willing to accept a 5% chance of being wrong when we publish, right? A lot of times you'll hear alpha is equal to 0.05, right? Chance of being wrong is 5%. What does that mean? Chances of being wrong is 5%. That means if you did 20 studies and they all had a chance of being wrong is 5%, that means 1 out of every 20 studies would be just complete hogwash, be completely wrong, right? Or it wouldn't prove correctly what you're trying to demonstrate. right? And if you do 1,000 studies, that's, you know, 50 studies are wrong, and so on and so forth. And that happens all the time where somebody will do a study to find the result. Someone else maybe can't replicate it when they try it, right? Just because that result turned out to be the two results turned out to be so different between the two groups, but the difference turned out to be due to chance, not to be a real difference. That time he happened to sample this group and get an unusually low number, and sample this group, get an unusually high number. And then when he compared them, he thought they were really different when they were the same. That happens, but that's the nature of statistics. That's we're measuring things that we can't have a 100% certainty with. So what we're doing is we're trying to measure and control the likelihood of being wrong. Make that at least make that part predictable. How likely is it that we're wrong, or how likely is that we're more than this distance apart from the real result? So if we if we did this, if we sampled the population, uh, 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 I don't want to confuse things. I think we got a pretty good idea what's going on. So I'm going to keep my mouth shut before I say something that confuses things. Right. So I think maybe if we take another example and give that a try, that might be better. Okay. Oh, now okay. Now this involves sampling a proportion of the population. Let me see if I can't. Another washing machine. Why did I get into these washing machines? Yeah, I remember. I've been using these examples for a while. I'm not sure why I haven't replaced them yet. Okay. I just want to give you an example of this applied to a proportion. Okay. So now let's say that we want to know what the true population proportions of Americans who are willing to accept the cut in living standards to help the environment. 2010 General Social Survey asked a random sample of Americans how willing they were to accept a cut in living standards to help the environment. Out of 1,381 respondents, 49 said that they were very willing or fairly willing uh, 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 to accept a cut in salary to help the environment. Okay, a living standard rather, to help the environment. Okay, so what can we say about the probability that someone in the United States would say that they're willing to accept a cut in living standard based on that study? What proportion are willing to of the sample? This is a sample now, right? Right. Yeah. Let me clear this out. Right. How much was it? 496 people out of 1,381. 1,381. Okay, or about 36% of the population said that they were willing to take a cut in living standard. Okay, most people said no, right? But in this particular case, this survey of random survey of 1,381 respondents. What happened here? 1,381 respondents. Am I equating back there? Yeah, I'm still on. Okay. 1,381 respondents, almost 36% said they were willing to take a cut in living standard. Okay, so now, problem here is that truly representative? Does that mean that we know now the proportion of the entire population is that's willing? No, this is a sample just like any other sample. It just happens to be a yes or no question, a proportion, a binomial, right? It's not but if I were to, let's say for a moment that the true population proportion was 35%. Well, if I took a sample, half the time I would expect a result below 35%. Half the time I'd expect a result above 35%, right? Just by the nature of if the mean is really 35%, if the center is really 35%, half the time I'll get above it, half the time I'll get below it. Once in a blue moon, I'll get really lucky and get exactly 35%, right? So we can handle this just like any other proportion. The only problem now is we need a way to calculate a standard error for a proportion. And I'm about to give you one. Okay, so I'm going to draw this distribution of proportions. Whoops. What is this doing now? Go away. There, okay. Okay, so now my distribution of proportions is also going to be normally distributed, right? If I took repeated samples over and over again, half time be below and half time above the proportion, except this time I'm dealing with a proportion. Here's my proportion. Okay, I'm going to call it 36%. Okay, so half the time, in this case, I got a proportion of 0.36. Right. So now I need a standard error. I need a way to calculate a standard error. I think I gave you something in there. Um, 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 what is the sample proportion? What is the sample proportion that would accept the kind of? We got that. Is the sample population proportion equal to the sample proportion? No, right? Sample proportion is the estimate of the population proportion. Calculate the standard error of the sample proportion. Well, we're going to calculate that by using a formula: the square root of P, the probability of them saying they're going to take the cut, times 1 minus P, the probability they say they won't, over the sample size. So let me write that formula down. It's equal to the square root of P times 1 minus P over the sample size N. What's our sample size? Did we say what it was again? 1300 and 1390, what was it? 81, 1381. Okay, good. So let's solve this. Standard error is equal to the square root of 0.36 times, what's 1 minus that? 0.64, right? Divided by 1381. Okay, the whole thing gets resolved first before we do our square root. And now I got to go through the hunt for my calculator again. I need a bigger screen. I got this nice 27-inch monitor at work that I can spread stuff all over the place. It's a little hassle working on this little screen. That you see it as a big screen, but in front of me it's just this 12-inch or whatever it is screen. Okay. Okay, so what is that? That's 0.36 times 0.64. Okay, comes out with a number like that. That looks right. Divided by 1381. Okay, is equal to, well, kind of a small number there. Okay, but what have I not done to this yet? I haven't found the square root of that yet. So I'm going to find the square root of this number. Okay, square root. And the square root is 0.0129. It's 0.013 roughly, about 1.3%. So my standard error is equal to, and again I'll round it off, is equal to 0.013. I'll round it off a little bit. Okay, so now 1.3%. So now, what's my confidence interval for my proportion? Well, why would this be any different than any other normal distribution? Except I'm using P as my center or my mean, right? Okay, so I'm going to use P plus or minus, right? 1.96 times my standard error. So P is equal to, let's see, 0.36 plus or minus 1.96 times 0.013. Now I'm gonna make things a little simpler for myself. I'm just gonna say 2 times 0.013. Okay, so it's 0.36 plus or minus 2 times that is going to be 0.026, 2.6%. So my confidence interval is going to be 36 plus 2.6 or 38.386. Okay, on the high end, and on the low end, I'm going to be subtracting that, so it's going to be 33.334, right? So my confidence interval is 0.334, 33.4% to 38%. So what does this tell us? Before, the study told us, it looks like about 36% of Americans would agree to a cut in living standard, right? What does this tell us now? Well, that didn't give us any kind of precision, any kind of way to compare this to something else. Now I can say, by using the standard error, I can now say that I'm 95% sure. It looks like it's around 36%, but with 95% certainty, I can say it's between 0.334 and 0.386, right? So now let me ask you an interesting question, okay? What if I wanted not 95% certainty, but 99% certainty? What would I do now? Exactly right, okay? One of you at least has taken this course before, okay? You didn't think of that now, right? Okay, good. You'd may worry me if you ever just figured this all out on your own without needing a statistics book. I'd be concerned, but for my safety. So at any rate, for my future employment. So at any rate, so now, if we want to be more certain that we captured the mean, here's our range, 0.334 and 0.386. I want to be more certain that I capture the actual mean between those two numbers. Do I want to get wider or narrower? I want to get wider. So if I want to have a higher level of certainty, my confidence interval has to be wider. If I'm willing to accept a lower level of certainty, my confidence interval can be narrower around my sample result. Okay, so let's take a look. I'm going to let's do it for 99%. Okay, I'm going to bring these numbers over with me, 0.36 and 0.013. So we got another piece of paper. Well, no, I ran out of paper. Okay, here's my. Okay, and this was 0.36. And let's see, my P was equal to 0.36. And what was my standard error again? It was 0.013, right? Okay, that's what we calculated from before. Nothing's changed. Sample size has changed. Everything else. But now I want to be more certain that the range that I come up with captures the true population proportion, right? I want to have less chance of being wrong and missing the population proportion in that range, right? So I need to have a wider interval. So now if I look at this, let's say I want to be 99% certain, right? Well, 99% certainty, I would need to have 99% of the area in here with only 1% outside of my distribution, right? Only 1% in the tails. That would mean that this end would have to be 0.005, and this end would have to be 0.5% for 0.005. Well, since I know the z-scores are going to be the same, just one positive, one negative, because it's symmetrical, I'm going to go to my z-table and see what z-score I need in order to get 0.005 in that area. 0.005, 0.003, 0.004, 0.005, let's see, 0.0050. Somewhere 0.005, somewhere around here. I'm gonna pick this number right here, 0.0049. It's 0.0051 and 0.0049. I'm just gonna pick this number because I don't need that many decimal places. So what does my z-score have to be to have only 5% in the left tail? It's gonna have to be negative 2.58. Right, 2.58. Okay, you're gonna be using these numbers all the time now. So the z-score down here is negative 2.58, and the z-score up here is going to be positive 2.58. Okay, if I go back to that table, you'll know if I go to the positive side, and you'll get an area 99.5%, only 0.5% left on the other end. Okay, so now when I calculate my confidence interval, and this could be just as easy, it could be x bar plus or minus 2.58 times the standard error, or if it's a proportion, it's p plus or minus 2.58 times the standard error. So for this problem, which happens to be for a proportion, right, it would be 0.36 plus or minus 2.58 times 0.013, 0.013, right, and or 2.58 plus 0.013. And I get my calculator out, and I'll give them a try. Clear. Okay, and it's going to be 2.5. I'm going to clear my memory here too because I was using that before. 2.58 times 0.013 is equal to this number, Did I do that right? Yes, it is. Plus, okay. I'm going to put that in memory. Plus, and I'm going to clear this. And I'm going to say 0.36 minus that quantity is going to be 0.0326, 0.0, oops, 0.326, 0.326. And the upper range is going to be, I'm going to clear that, and it's going to be 0.36 plus that amount. That's going to be equal to 0.39394. Okay, so this range is wider than the 95% confidence interval. Okay? The other range was narrower because I was willing to accept 5% chance of missing the mean. So if I want to have more confidence, the confidence interval becomes wider. The reason why it becomes wider is because the z-score that I use in this formula is bigger number. Now, if I were willing to accept a 90% chance, if I wanted a 90% confidence interval, I was willing to accept a 10% chance that when I give you this range, that the true population proportion or mean, whichever one we're using, is outside of that, then I would use a z-score that's smaller than either one of these. Smaller than 2.58, smaller than 1.96. Anybody want to look on the z-table? Tell me what you would use as a z-score for a 90% confidence interval. 5% tail on the left, 5% tail on the right. What would that number be? I'll get the table up. I'll tell you what, I'll get the table up for you so you can see it. It's going to be on the low side of this, so I'll have to crank this up a little bit. See what it is? For a 5% area? There's a 5% area. It's going to be, where's the closest one for a 5% area? 1.64, right? So you're going to multiply 1.64 times the standard error, add and subtract that to whatever your sample mean was, right? Pretty elegant, right? So now we have a mechanism not just of taking a sample and finding a mean or proportion, but also now predicting what level of certainty that we will find the mean within a certain range around that number, right? So that really helps us quite a bit, in terms of describing to someone what our certainty is about this, what our level of uncertainty or certainty is about this. Yes.
Is there a way that people decide whether they want 99%, 95%?
Yeah, for most of you guys, it's going to be basically what we ask you to calculate, right? Like on a test or something like that. But yeah, of course. I mean, it's kind of the default for most of these kinds of studies is 5% chance of error is acceptable, right? So later on, when we start going to talk about things called alpha error, beta error, power, so on and so forth. We're going to have all these new terms, like in terms of like what our level of certainty is. Usually, in most studies, you see them say, "Oh, we proved this to this level, and that level is 95% certainty." Or more frequently, they'll describe it as less than a 5% chance of having a result like this being due to chance and not to a real difference. So, in other words, 5% chance of being wrong. So, 95% confidence interval is kind of like the default. That doesn't mean that, like, if it's something really important that you don't want to get wrong, that you might not want 99% certainty. Or if you're really desperate to publish, you might not be willing to settle for 90% certainty, right? So yeah, that's a judgment call, really. But most often you see 95%. Okay, so I think this is a good time to break. You can try that other example that's on there on your own. And maybe when we go over sometime during the midweek, we'll set up a little session where I can go over the exam and we can either try the one that's in here or another example. Yes. Yep. Oh, okay. All right. So I want everybody to go out now to a tattoo parlor. 1.96, right? 1.64 and 2.58. Or 0.25. Yeah, 2.58. Right. You can get those tattooed. Put it somewhere where under your wristband. So that way, when you're in real life, civilized, you're not around epidemiologists. You're in civilized society. They don't have to know that you know that stuff. Okay. Any questions? It's pretty interesting, right? This has a lot of power now. We're starting to get into things. You can see now we're starting to see what we can do with a sample and understanding what the process of understanding the data that we can get and the level of confidence and the accuracy that we can deal with when we take a sample. We're starting to see that. We're really going to put that to work because that's what this is really all about. Is that when we compare, say, one group, let's say we're doing a drug study and we're comparing how that affects blood pressure to how placebo affects blood pressure. We want to know, did the difference between these two groups, the results of these two groups, what's the likelihood that that difference was due to chance, that we just happened to get a higher number here than we got here, right? That like the person that took the group that took the drug got a lower blood pressure. In other words, you take two groups that have roughly the same blood pressures. You give one a drug, you give the other a placebo. You go back, you test them after they take the placebo or a drug, and now you take it out, you test them again, that sample, right? Well, half the time one's going to be higher than the other, right? Even if there's no difference, they're not going to be the same again. They're going to be different. So if you do see a difference that the blood pressure is lower in the group that took the drug versus the placebo group, how sure are you that that difference is not due to just plain chance, and that it's a real difference and the drug is causing that difference, and not just pure chance that on that particular sample you got a group that had a lower blood pressure when you took it. Okay? That's what this is really all about. That's what a lot of this stuff is about, being able to demonstrate whether your result is really due to chance or really due to a real effect that you're having, and whether or not that effect is clinically significant, whether or not it's a big enough effect that it's really going to, improve public health or whether a drug really works and so on and so forth. Okay, good. Let's call it a night. Right? What have we done? We're about 7:48. We've got 2 minutes left. Take a deep breath. Hold up your computers. And you guys online, thank you for hanging on. Oh, yeah, you're awake. Good. Thank you very much. I'm glad to hear that. Even before I asked. Okay, great. Good. Very good. 1.6 and 1.7 are actually 1.64. Good. Very good, guys. And like I said, I'll set something up during the week. We can go over the exam, maybe do another example of this. I'll post something. Something that doesn't involve washing machines. Something a little bit more public health oriented.
Do you have an entry key for this exercise?
No, but I'll make one up.
Okay, thank you.
Because there is one example we didn't get to on there.
Yeah.
Yeah. Also, I'm going to change one of those problems so the numbers are a little bit more. I got a question here. Let's see. Does 95% that the X bar is within two standard deviations of the sample mean? Yes, that's what it means. Is that we're 95% sure that the true mean is within two standard deviations, two standard errors, really, of the sample mean. Not standard deviations population, but standard errors for that sample size. Okay, okay, guys. Good night. Bye.